Welcome to another podcast from SnazzySurgeon. Today we're taking a deep dive into the foundational architecture of the hand skeleton. For us as surgeons, planning reconstruction or even just fixation, understanding how this underlying framework supports both powerful gross action and, well, simultaneously enables those intricate fine movements. That's the unique challenge we have to master, right? It really dictates everything from plate placement to tendon transfer design.
Exactly. And when we talk about optimizing function, we aren't just looking at the dynamic elements, the muscles and tendons. We must first understand the pure architectural basis of function. I think our mission today is to really get a grip on the constraints the skeleton and those critical restraining ligaments impose, arguing basically that grasping the concept of the fixed and mobile segments is the fundamental prerequisite for any successful intervention. It's really the difference between a hand that just works and a hand that truly performs well.
Okay, let's unpack this. Using that conceptual division of the hand skeleton into 4 elements, I think that was Littler's concept, wasn't it? The most critical starting point is always the fixed unit, which acts as our sort of central and unmoving reference point. What defines that fixed core?
Right. So the fixed unit is that solid, unmoving center of the entire structure. It's composed of the second and third metacarpals combined with the entire distal carpal row. This central beam, it's rigid in both its transverse and longitudinal axes, and it forms the stable foundation around which the 3 mobile units can then operate. That stability is absolutely key for leverage.
Okay, makes sense. And what are the 3 mobile elements we need to think about surgically?
Well, first, obviously, we have the thumb and its metacarpal. It's defined entirely by its really wide range of motion at the carpometacarpal, or CMC, joint. It's the most versatile segment, for sure, and its positioning and activity are influenced by a pretty complex motor group. 5 intrinsic muscles and 4 extrinsic muscles.
Wow, that's a lot of motors just for one digit.
It really speaks to its functional necessity, doesn't it? Second, we have the index digit. Now, while it shares the fixed stability of the second and third metacarpals proximally, its unique characteristic is its independence of action. This lets it work precisely against the thumb. It's supported by 3 intrinsic and 4 extrinsic muscles.
Okay. And finally, you mentioned a stabilizing vise.
Yeah, that's the stabilizing unit. This consists of the 3rd, 4th, and 5th digits, and functionally, we group them with the 4th and 5th metacarpals. Its purpose is sort of twofold. Either it acts as a static platform, that stabilizing vise you mentioned, holding objects while the thumb and index do the fine manipulation, or it contributes forcefully, in concert with the other units during powerful, gross grasp.
Right. Now, if we zoom back into that fixed unit, the structural genius really lies proximally, doesn't it, in the wrist? If we look closely at the architecture of the distal carpal row, we see it forms a structurally solid transverse arch. It's perfectly balanced, with the large capitate bone acting as the absolute keystone, really locked into position.
That analogy of the keystone is perfect, because much like a Roman arch, that strength is maintained by compression and, importantly, ligamentous restraint. Specifically, this incredibly strong, fixed transverse carpal arch is meticulously maintained by the powerful interosseous articulations between the distal carpals, the dense intercarpal ligaments, and of course that incredibly important transverse carpal ligament.
Which we all know clinically as the flexor retinaculum.
Exactly. That whole mechanism generates an incredibly rigid proximal foundation. It's essential for all the subsequent distal mobility.
And this rigid foundation then projects distally via those central metacarpals, the second and third, creating the fixed longitudinal arch based on their anatomical convexity. So that central beam, that fixed unit, is stable, which means it has to be positioned correctly for everything else to work effectively.
Precisely. This central beam, unlike the mobile units, moves monolithically like a single block at the wrist. And its positioning is entirely controlled by the major wrist movers, which, critically, insert directly onto the second and third metacarpals. These motors include the prime wrist extensors, the extensor carpi radialis longus, ECRL, and extensor carpi radialis brevis, ECRB, and the prime wrist flexor, the flexor carpi radialis, FCR.
That's fascinating. So if all those muscles insert right there, they really define the operational position of the whole hand. But wait a second, if the flexor carpi radialis is a powerful flexor, why are we grouping it with 2 extensors when we talk about the overall positioning and stability of the central unit? That seems a bit counterintuitive.
Yeah, that's a great question, and it really speaks to the complex balance that's required. While the FCR certainly acts as a prime flexor, its centralized insertion right on the second and third metacarpals means it actually helps stabilize the longitudinal position of the carpus when the concerts are contracting. It provides a sort of counterforce that's necessary for fine-tuning grip.
Yeah.
However, you're right. In terms of setting the primary posture, the extensors definitely dominate.
Okay, I see. So if we had to really focus specifically on the single most important motor operating that central hand beam at the wrist, the one that truly dictates the necessary initial positioning against gravity, which one would it be?
Oh, hands down, it has to be the extensor carpi radialis brevis, ECRB. Clinically, it's the absolute workhorse. It's the muscle that works continually against gravity to position the pronated hand into that critical extended position needed for effective grasp and manipulation. If you lose the ECRB, you essentially lose the stable platform. It is the critical motor for dictating the central beam stability.
Got it. That really provides the context for the fixed part. Okay, let's shift our focus now to the hand's adaptive genius, its mobility. Although the distal carpal row is fixed, as you said, when we move distally to the level of the metacarpal heads, the transverse arch suddenly becomes mobile. That allows the hand to cup and conform, right?
Yes, exactly. The hand transitions from this rigid block into an articulated tool. And the structure that really initiates this adaptation is the thumb. The first metacarpal articulation with the trapezium, the CMC joint, is that shallow, saddle-like articulation, and it's the loose capsular ligaments that allow for that remarkable range of circumduction.
But that range needs control, doesn't it? Otherwise, it would just be uselessly floppy. What checks this extensive excursion?
Right. Its stability and range are critically checked by specific capsular thickenings, including the crucial, often cited volar beak ligament. And moreover, its mobility is constrained dynamically by muscular attachments and the soft tissues that kind of tether it to the fixed axis. We're talking about the adductor pollicis and the first dorsal interosseous, alongside the inherent resistance provided by the fascia and the skin of the first web space. These structures define the functional limits of the thumb's motion.
Okay. Turning to the ulnar side then. The mobility of the fourth and fifth metacarpal heads is maybe less dramatic than the thumb's, but it's absolutely necessary for creating that concavity needed for cupping the hand. How restricted are they compared to the thumb?
They exhibit limited but absolutely critical mobility. They move dorsally and palmarly in relation to that central hand axis, with the movement occurring at their respective CMC joints. This allows the ulnar border to essentially fold inward. What's anatomically interesting here is their tethering mechanism. They're held together, but allowed movement by the specialized intermetacarpal ligaments. These unite adjacent metacarpophalangeal volar plates, which are themselves an intimate part of the joint capsules.
So this inherent controlled mobility then allows for the active creation of the functional transverse metacarpal arch. When the intrinsic muscles fire, this arch approximates a semicircle, really turning the palm into a cup.
That's exactly it. This action is achieved by the sort of antagonistic pull of the mobile components. You've got the thenar muscles, supplied by the median nerve, palmar abducting the first metacarpal, and simultaneously, the hypothenar muscles, supplied by the ulnar nerve, palmar abduct the fourth and fifth metacarpals. It's a really finely coordinated muscle synergy.
But let's think about this clinically. What happens when that synergy is lost? The mobility is now dictated solely by the extrinsic forces, right?
Yes, and that's where it becomes highly relevant to reconstruction. When the thenar and hypothenar muscles are relaxed, or worse, paralyzed, the extrinsic extensor tendons will just pull those mobile metacarpal heads dorsally. This is the moment of pathology. Flaccid paralysis of the intrinsic muscles, which we commonly see in combined median and ulnar nerve palsy, results in the loss of active cupping. Structurally, this produces a flattened or even reversed transverse metacarpal arch.
And that loss of the active semicircular arch, well, it destroys the hand's single most important functional signature, the proper circumferential arrangement of the MCP joints, which is necessary for convergence of the fingers in flexion. I mean, if you can't cup the hand, the fingers just can't converge correctly to form that cone shape required for effective gripping.
Exactly. And this essential functional convergence actually allows us to precisely define the anatomic center of the hand. It's quite neat, actually. When the fingers fully converge to form that cone shape, the apex of the cone lies directly over the anatomic center. If we were to drop a vertical line from that apex down to the center of the base, it strikes the third metacarpophalangeal joint. That point is the geometric center of functional grip.
That's a really powerful geometric principle. So to tie it all together, if the fingers are fully abducted, the fingertips form radii of equal length from this same anatomic center, the third MCP joint. And if that radius is projected proximally, you're saying it falls exactly at the wrist joint. The geometry is that fixed?
Absolutely. It just shows that the hand, despite all its complexity, operates around a precise, predictable spatial reference point. And just to circle back one final time to the ECRB, we established it as the critical motor for central beam positioning. Well, anatomical studies show that even in the absence of any other motors, say in total intrinsic paralysis, the ECRP is still active enough to pull the central third metacarpal into extension. This makes it the apex of the passively created transverse metacarpal arch. It reinforces that central axis constantly, acting as the foundation for both active and passive positioning.
So, okay, what does this all mean for us clinically? The relevance seems profound. Surgical success and hand reconstruction, it seems, hinges entirely on respecting the rigid foundation of that fixed unit and then restoring the dynamic interplay of the mobile units, particularly ensuring that intrinsic muscle function is adequate to maintain that functional transverse arch and, crucially, the correct convergence geometry.
Which raises an important question for you, the listener, to perhaps consider. Knowing that the precise geometric center of functional grip is the third metacarpophalangeal joint, how does that geometric imperative impact your planning? Whether it's flap design, tendon transfer placement, or even just positioning the hand during a fusion, how do you ensure optimal gripping function postoperatively centered around that critical point? It really is the axis around which all function rotates.
Thank you for listening to our podcast. See you in the next episode.